looking at the effect of temperature on the reaction rate. How does temperature affect a reaction rate? Now, we all know that as we increase the temperature of every reaction, the frequency of collision increases and increases. Why does the frequency of collision increases? Because increase in temperature will ignite what? Or increases the what? The kinetic energy of the molecules. And the molecules begin to what? Collide. So, and once the molecule begin to collide, then it means that the reaction rate was going to be what? Increased. Now, the scientists that put forward or that proposed an equation governing this reaction rate, increase in effect of temperature on the reaction rate, his name was Arrhenius. Okay, I believe you have heard about this name. Arrhenius. Okay, Arrhenius was the scientist that proposed an important equation that governs the what? The rate at which a reaction proceeds. Okay, the Arrhenius equation, the famous Arrhenius equation, states that the rate constant is equal to the pre-exponential factor A multiplied by exponential minus EA all over what? RT. Now, let's analyze these parameters, okay? The K is called the rate constant, okay? This is the rate constant. This A is what we call the pre-exponential factor. Okay? Then we have EA is the what? Activation energy. R is universal gas constant. T is temperature. Now somebody will ask, what is the significance of this equation? Arrhenius was able to propose that if the temperature of a reaction is increased, if this temperature here is increased, the increase in temperature will cause the increase in this exponential. I repeat, if the temperature of a reaction is increased, the increase in temperature will cause this molecule, the exponential factor of this equation, to increase. And if the exponential factor increases, it means that the value for the rate constant will also increase. And if the value for the rate constant increases, then the rate of the reaction will also increase. Have you seen where the thing is coming from? It's coming from what? The temperature. So we're looking at the effect. What is the effect of temperature on the reaction rate? How does it affect it? This effect of temperature is being given by this what? The Arrhenius equation. So from this Arrhenius equation, we can be able to deduce more equations that are of importance in your calculation. Okay, so for us to deduce the next parameter, we are going to just quickly take the natural log of this expression. So if we take natural log of this expression, we are going to have natural log of K is equal to minus EA over what? RT plus log A. Okay, so what you're seeing here is the same thing as saying if I change this into normal logarithm, it's going to be log K is equal to minus EA all over 2.303 RT plus what? Log A. Okay, so this is a simpler version of the Arrhenius equation. So now we are going to consider that if we have two rate constants, K1 and K2, okay, and T1 and T2, that is different temperature changes. Okay, the first temperature is for K1. The temperature is the effect of this temperature on K1. The T2 is the effect of this temperature on what? On K2. Okay, so if we have this kind of equation, we can now combine these two things to arrive at a more complex equation that we can solve for any of these parameters anytime we are asked to do that. So in order to go ahead and do that, we'll simply have that, combining this thing, we'll have that log k2 over k1 is equal to EA over 2.303 RT bracket open T2 minus T1 all over T1 T2. So I don't want to come and start showing you or proving how we got this equation, okay? We got this equation by combining, taking this one as if you have K1 and K2. Let's say we have this expression now for K1, the other expression for K2. Combining the two equations together, you come up with this. So this is an equation that you can use to solve any of these parameters. Remember the K2 is the rate constant for this T2. The K1 is the rate constant for this T1. This is the activation energy, the minimum amount of energy you need to overcome for you to undergo a reaction, okay? Then this is the universal gas constant. We have talked about these things here. So with this equation, we can attempt some questions to see if we can be able to solve some problems with this, okay? So this is what we call the Arrhenius. This is the proper Arrhenius equation, okay? This Arrhenius equation, these are all Arrhenius equations, but this is a simplified version of the Arrhenius equation. I have to clean this, okay? There's no T. We already simplified the T, which is this, okay? So take note. So if you simplify this equation, you have this. So this is what we call the Arrhenius equation. Cut. So let's look at this simple problem on the Arrhenius equation, okay? So they said that the rate constant for the first order reaction at 35 degrees C is twice at 25 degrees C. The rate constant for the first order reaction at 35 degrees C is twice at 25 degrees C. So what this thing means is that if you have K1, if K1 is K, then K2 is twice K1. Okay? So from this question now, we are given this temperature is the temperature for, they said the rate constant of the first order reaction at 35 degrees C is twice. So I'm going to take this as the T1 and this as the T2. So for T1 becomes 35 degrees C, convert it to Kelvin, plus 273 Kelvin. 273, I think this should give you 308 Kelvin. Okay, then the T2 will be 25 degrees C, convert to Kelvin, you have, this should give you 298 Kelvin. Okay, so you're not asked find the activation energy, so we are looking for activation energy. Okay, so what else was given to you? They say we should take R as 1.987 calorie per Kelvin per mole. So take note, so the R will be given us in calorie. So if the R is in calorie, it means that the activation energy will also be in calorie. If the R is in joules, or is in joules per mole per Kelvin, remember this thing you are seeing here, this R we are seeing here as 1.987 calorie per mole per Kelvin. Okay, it's the same thing as saying R is 8.314 joule per mole per Kelvin. Okay, if you convert calorie to joules, you will get this. Okay, 1 calorie is equal to 4.182 joules. So you can actually convert calorie to joules by multiplying by what? That constant, 4.182. So to solve the question, we are going to invoke the Arrhenius equation, right? The Arrhenius equation is saying that log K2 over K1 is equal to EA all over 2.303 R into T2 minus T1 all over T1 T2. Okay, so we invoke the Arrhenius equation. So we just plug in the values. Okay, so we have that log, what is K2? K2 is 2K1, so we have 2K1 over K1 K1 is still, K1 is K, sorry. That's, yeah, 2K. Please take note, K1 is equal to K, so K2 will be equal to 2K. Okay? So this is K like this. So K cancels K, equal to, what is EA? EA is unknown. So we have that EA all over 2.303 times 1.987, okay, into T2 is, where is T2? 298, T1 308. So T2 is 298 minus 308 all over T1. T1 is what is T1? T1 is still, yeah, T1 is still 308, okay? 308 times 298. You close. There's a correction we need to make immediately, okay? So let's go back to the question. There's a correction we need to make. So they say the rate constant for the first order reaction at 35 degrees C is twice that of, there's a mistake here, it's twice that of at 25 degrees, that of at 25 degrees, okay? So meaning that this is T1, this is T2. So T1 is this, I'll change it, okay? So this is T2, this is T1. So take note of the correction so that we'll have 308 minus what? 298. So that here will become 298 times 308. Okay? So that is the only correction I want to make here. So take note T2, take note T1. So when you have this, so every other thing remains the same. So the T2 is going to be the 2K, so whereas K2 is still this, and K1 is still this. Okay? So K2 is still what you are trying to say. So from here now, we have that, this cancels this, we have log 2 is equal to EA all over, multiply this and this. What are we going to have? When we multiply that, we have 4.576 into this minus this should give you 10 over this times this will give you 91784. Okay, so we'll proceed. So you simplify this, you simplify that, and then also divide it with what? With this. If you simplify this and divide it with this, you have that log 2. What is log 2 first? Log 2 is 0.3010. Okay, so dividing this, you have an answer, and dividing with this under, you have that EA. So from here we have that, okay, let's quickly just do it at the top. We have that 10 EA all over, multiplying this and this, okay, we have the value to be 4200003.584. Okay, so you can now make EA subject of what? Formula. You can make EA subject of formula. So if I make that EA subject of formula from here, so I'll have that EA will be equal to this times this divided by this, right? This times this divided by this. So I have that 0.3010 times 4200003.584 all over 10. Okay, so when you divide this, you will now have the answer. So this should give you 1264.2 calorie. This is the answer. So the activation energy for this reaction is 12642 calorie. So look at the solving. It's a very straightforward solving. Okay, the K1 was not given, the K2 was not given, but they say that K2 is twice K1. Okay, so it's going to be 2K. If K1 is K, K2 will be 2K. So you have this already. Then the T2 was 35, T1 is 25. convert to Kelvin, you have this. EA, we are looking for it. This one was given to you, the universal gas constant R was given to you as 1.987. Okay, so and I told you already that they can give it to you in calorie or in joules. Anyone they give you will determine the final answer of what you are looking for. Okay, so log K2 is equal to this is the Arrhenius equation. Okay, so we plug in the value for K2. K2 is 2K. We put it here. For K1, K1 is K. We put it here. Okay, K cancels K, you have only 2. So log 2 is 0.3010. Okay, or just say 0.301. Now, the next thing here, we are looking for this unknown. T2, 308. T1, 298. Subtract. T1 is still 298. T2 is 308. Subtract and multiply this. Okay, you have this and this here. Okay, then this times this, you have this. Then this times this, you have this. Then 10 times E, you have 10 EA. So you now make EA subject of formula. That's how we got the final answer here. So this is a very simple calculation from the Arrhenius equation. So there are more examples. When you check the app, you will see more examples that you can practice with. Okay, go to past questions and go through those questions. You understand some of those things because they are all revolving around this equation.